Bismillahirrahmanirrahim. Assalamu alaikum. I'm Dr Farhad Ali, your instructor for the course of Theory of Fluid. I hope you will have this lecture in very good health. Uh, in today's lecture, or the lecture for this week, we will discuss a method of description. So we already discussed these methods in the previous lectures, and we have discussed little bit about these methods. So you can see in the previous lectures, in the slides, you will have a link. I have provided a link, and you can see for further explanation, you can watch those videos by clicking the link. So I hope you have gone through the previous lectures, and you have watched the provided videos to support your lectures of this week and also of the previous week. So in the previous lecture, shortly we have discussed the methods of descriptions. So today I will discuss the method of descriptions, and also visualization of flow pattern. So let me start from the methods of or descriptions. As you can see that we have two approaches while consider the flow problems. Okay, so one is Euliern approach, and the second one is the Lagrangian approach. So in the previous lectures, I have mentioned that I have already discussed shortly these two definitions in the slides, but that explanation was not enough, so that's why I have included this topic in the today's lecture. So these two approaches are Euliern approach and Lagrangian approach. So we consider a divergent channel. Divergent channel means that you can see that uh, here the channel diverges. Okay, you can see the the two you can see the two plates are the two edges or boundaries. You can see they are diverging, so we call such channel as a divergent channel. And you can see that in this channel, if the flow is in x direction, so this is the inlet of the flow and this is the outlet. So you can see in the inlet are the fluid particles which enters this region, this channel. You can see the magnitude of the velocity, and you can see, look at here, so the fluid velocity in the divergent channel is decreasing while moving towards the x-axis in the x direction. Actually, in the increasing x direction, the velocity gradually decreases. You can see the magnitude of velocity here and here. Okay, so here the velocity is greater as compared to here at this region. So and also you can see that in y direction, in this direction, the magnitudes are same in inlet and also in the outlet. This magnitude is same with these are the velocity, the fluid particles velocity's magnitude. So this magnitude of velocity is same to this one, this one, this one. So there is no change in the y directions. Okay, only changes in the x direction. You can see the magnitude of velocity from this arrow. So this arrow is uh, larger as compared to this velocity. From the length of the arrow we can decide. Okay, so we consider this divergent channel, and we have fixed a probe. This is probe, okay, some device at this point A which will study the properties of fluid particles while passing through this probe. Okay, this probe is a device which may measure the velocity of the fluid particles at this position or the density of the fluid particle at this position, the temperature of the fluid particle at this position. So we call this probe. Okay, so we fix a probe at this position A and we will study the fluid property at this position. So if we have a probe at a point A, this measures the properties of different molecules, but at one point. This called the Euliern approach. Okay, it studies the fluid particles. This probe studies the fluid particle only at this one part on this one point. Okay, if the temperature of the fluid particle at this position, so we don't care about the fluid particle here, okay, and are here. We just mere our focus our observation to this point, and when the fluid particles pass through this point, so we measure the properties of fluid, that is what is the velocity of the fluid at this position, what is the density of fluid particles at this positions, what is the temperature of the fluid particles at this position, what is the mass flow rate at this position. Okay, and once it passes to this point, we don't care about the properties. So we are just focusing on to this point. The fluid particles comes and pass to this point, comes and pass to this point, and we just focusing to this point. So such approach while studying the flow problems are called Eulerian approach. We call this Eulerian approach. Okay, so look at this one. We will consider a region, and look at this one. Let's say this is a region. This is the point A, and this is the fluid coming. So the fluid coming maybe in this position, maybe in this position, but the fluid which passes through this area, we are our focus of our point of observation is this region. So we will study the fluid properties at this region. Our focus will be only on this region. If it cross this region, so we don't care about the properties. Or if the fluid is here, so we don't care the fluid properties. Okay, we just study the fluid properties which enters or leaves these regions. Okay, so for example, if this is a region, while you focus on a, okay, in inside a river, and you just uh, observing that how many fish enter this region and how many fish leave this regions. Okay, only your observation is this region. Maybe there is the river is also beyond this point in all direction, but we don't care the the fish activities or properties at this position. Okay, only we are focusing on at this position. So such type of approach, while we study the fluid properties, are said to uh, Eulerian approach. If the if the probe moves with the fluid particles, okay, with the fluid molecules, with the fluid particles, if the probe, that device which mere record the properties of fluid particles, if this recorder, if this probe or this device moves with the fluid particles and it is attached to the molecule or a particle, if this device is attached or tagged with the particle, and when the particle moves, this probe is also moving, then the probe measures changes of the properties of a particle which moves around the fluid. So this approach is called Lagrangian approach. Okay, so you can see that in this case, in this approach, the we did not focus on a region, but we focus on a fluid particles, not a region. Okay, the previous approach or concept was a region, but in this case you can see this uh, in this case we just focusing on individual molecules. Okay, so this approach is called a Lagrangian approach. Okay, so you can see that um, okay, if we have particles in a fluid, in a velocity field or in a fluid, okay, so we have many particles. These are the fluid particles. Okay, and this particle is moving in this flow field. Okay, this is the flow field. Okay, these are the flow fields, sorry. These are fluid particles, and we call this the flow field. Okay, this is the flow field, the fluid particles moving in this direction. These are some lines, we call these streamlines. Okay, so the fluid fields, and it is moving in these directions. These are the fluid particles. Okay, and we want to study the fluid properties, these molecules, the fluid particles properties. So how we will study these properties? We take a probe here. Okay, let's say with this molecules. Okay, and let this is some probe, and while the molecules moving, so this probe is, look at this molecules. When this molecules reach to this position, okay, so the probe also will be, okay, in this position. And when the particles moves in this direction, this probe will also move with the fluid particles. So now you can see we do not focus on the region, but we have attached a probe with these particles, and when the particles is moving, so the probe is also moving with the particles, and uh, it measures the properties of the fluid particles. Okay, so when this fluid particle is moving here and there, so the same, this probe will move with this fluid particles, and it will mirrors the fluid properties, unlike the previous one, which we just focus on the region. We don't care. The probe was fixed, the device was fixed, and the fluid property were while passing through the fixed probe. But in this case, the probe is not fixed, the probe is moving. Okay, and the fluid and it means only those the property of those fluid particles which is attached, to which this probe is attached. Okay, so in other words, you can see, in the Eulerian approach, we study the region, but in this case we study the individual particles. Okay, so uh, in this case, this is just example. While you are um, on the boat, okay, you are in the river, okay, while using the boat, and the fish is moving, and you are just following that fish to observe its properties, its activities, while the fish move in left side, so your boat is also move in the left side. That is, your boat is just like a probe. Okay, you are following, the fish. When the fish moves in the left side, you also turn your boat to the left side. Okay, okay, so you can see, okay, if it moves in this direction, so your boat is also moving in this direction. And if it uh, turns to this direction, okay, to the right direction, your boat is also turned to the right direction, and you are just following the movement of the fish. Okay, so this approach is called the Lagrangian approach. Most of the laws, conservation laws, Newton's second law, these are in the frame of Lagrangian. Okay, because the Lagrangians, you will see that it only change with respect to time. Okay, so most of the laws are in the frame of Lagrangian, but experimentalists do not interest in the Lagrangian approach because uh, it is not physical possible to study each and every molecules. As in the previous lectures, in the previous lecture mentioned I have explained that only in a small uh, full stop or a dot, a very small dot, infinitesimal small dot can accommodate thousand of particles, thousand of water molecules. So uh, even if you uh, study the properties of molecules uh, in the area which is equal to the size of the grain of sand, so you will find 1,000 of molecules and you will not be able to study each and every molecules. So actually the concept of the Lagrangian is actually the concept of the individuality, that you have to study each and every molecules. So experimentalists do not interest, or for them it is not possible, to study each and every molecule. So they fix a region, and in that region they studies the properties of molecules of the fluid particles. So but as all the laws are in the Lagrangian approach, so as we discussed that it is not physical for the experimentalist, so we have to change this approach or these laws to from the Lagrangian to Eulerian approach. Okay, so uh, we want to know how to relate changes in the Lagrangian approach to change in the Eulerian approach, or to transform the Lagrangian approach to the Eulerian approach, because the physical, the approach which is more physical is the Eulerian approach, or the approach which used by the experimentalist is the Eulerian approach, not the Lagrangian approach. But the laws are in the Lagrangian approach, so then how to transform these laws into a Eulerian approach? So we have to relate these two approaches to each other. Okay, so most of the fundamental laws are in Lagrangian framework. As I have mentioned above, the fundamental laws means F is equal to the second law of motion. So you can see the second law of motion. It is given in the Lagrangian form, and you can see F is equal to ma. Okay, and actually this is equal to F is equal to m dy by dt. Okay, so you can see this is uh, a Lagrangian approach. Okay, you can see uh, it is only the function of time. And if, for example, I have already mentioned this, that if look at this dot, inside this region there are thousands of molecules. To study each and every molecules, for example, you have to apply this laws. If I equal to mi, okay, or if the mass is constant, so then you have to dvi by dt. Okay, so are different molecules. So you can see only let me write the mi, then it will becomes this formula will becomes fi and mia. Okay, so f1 m1a, f2 m2a, f3 m3a. So you have to apply thousand of you will get thousand of equations. Okay, if you study the molecules, the nature, the stresses, the forces which acting on these molecules. So if you study the Lagrangian approach, so you have to to study each and every molecules. You have to fix a probe to each and every molecules, and it will study the properties of fluid particle of these particles. So individuality is not physically uh, possible. Okay, because when you say that 1,000 molecules and you applied for each molecule this equation, so you will have thousand of equations. And when you have thousand of equations, so how you it is not humanly possible to study the thousand of molecules, sorry, of equations. Okay, it will gives thousand of governing equations. Okay, so there will be thousand of unknowns. Okay, so it would not be possible to study the Lagrangian concept or approach. So what we should do, okay, to uh, avoid this or to get rid of this approach, because the laws this law is given in the Lagrangian approach, then we have to do something and to change this to the Eulerian approach. So there we have some relation uh, between these two approaches. So now we want to apply these laws in the Eulerian framework. Okay, so we will relate or we will transform the Lagrangian framework to the Euliern framework. Let's relate the observations using these two approaches just for an infinitesimal region in space, point in space, which I have already shown that just it is a point occupied by an infinitesimal object. Okay, we consider a region, in other words, just like a point. Okay, and that space, that point is occupied by an infinitesimal object. Let's focus on the temperature in system. Temperature is the function of space variable as well as time. Okay, and if the probe is taken to a particle, temperature is x of tau, y of tau, and it is only the function of tau, the time. Sorry, the time. Okay. Okay. So you can see uh, the change in temperature. The change in temperature is, if it is in the x direction, it change in the x direction, but it is with respect to time. If it is change in y direction with respect to time, the change in temperature of the particle in the z direction, okay, with respect to time, and also it will show the temperature with respect to only, okay, with respect to time. So when it moves in next direction and you are studying that what changes occur in temperature of the particle with respect to time, when it moves in y direction, and again you are following these particles, and with respect to time you are observing the changes in temperature of this particle, are when the particle is moving in the z direction, and you are studying the temperature difference or temperature changes with respect to time, and then just okay with respect to time. Okay, so mathematically, if we write this discussion in mathematics, so that is the temperature dt by dt. This t is time and this t is temperature. Rate of change of temperature of a fixed particle. Okay, this is only we have considered only a fixed particle. So it means dt by dt, the rate of change of temperature of that particles. Okay, just like we have considered that this is the region, this point, and at this point we have considered an infinitesimal object, and we want to study the temperature. Okay, uh, while we uh, take a probe or attach a probe to the particles. Okay, so when the particle moves in the x direction, in the y direction, and in the z direction. Okay, so we are following the fluid particle. First it moves in x direction, then y direction, or in the z direction. Okay, that what changes occur while it is moving in this direction in some time t. Okay, while what changes will occur if it is moving in y direction with respect to time, and in the z direction what changes occurs in the fluid temperature, particle temperature, in the z direction with respect to time. Okay, so uh, we call this, and also with respect to time. Okay, this is in the z direction, in the y direction, in the z direction, in the x direction, but also we can measure the changes, that what is the total change with respect to time. Okay, so uh, this approach, you can see, when we say the individual particles, if you study the individual particle as we have considered the fixed one particle, so this is called the Lagrangian approach. And now we have to change this to the Euliern approach. Okay, to transform the individuality to a point, to study a region, a fixed region, not a fixed particle. To transform, this is the way to study a fixed particle, to study individual particles, and we have to change this to a fixed region, not a particles. That we will consider just a region, and we will focus on that region, and we will study the fluid properties. Okay, so this is the difference between the two. This is actually the change in the individual particles. What is going on? Okay, what is its velocity while it is moving in x and y direction? You are following it. Okay, for example, when you following someone, okay, if you are just like a spy, you are actually observing someone activity, and when someone is moving in different directions, okay, you are just following his or her activities, so you are just following that individual. So this type of approach is called the Lagrangian approach. But the other approach is the fixed point, that you are just uh, standing at a point, or maybe in a square. Okay, um, or in some roundabout, and you are studying the mob of, for example, the number of vehicles. You are studying the number of vehicles while standing at a fixed point in a square or in a roundabout. So that type of study will be Euliern. If you just want to focus on a specific type of vehicle, that I have to study the property of just that individual vehicle, you focus some probe on that vehicles, and the vehicle is moving in round about the Peshawar city. and that probe is following that vehicles. So this approach is called the Lagrangian approach. So mathematically, the Lagrangian approach is shown from this one. Okay, and also you can see the changes in the x direction, but with respect to time, the change of as I have shown this, you can see the temperature uh, changes, but if it is in the x direction, so the change in of x with respect to time. Okay, so what is changes occurs in x direction with respect to time. So you can see this is the chain rule I'm going to apply. This is the change in temperature in x direction, and look at the change. Then uh, the change in x with respect to time. So we can cancel these two, this one and this one, and we will have the same thing. Okay, this is the total. We call this the total derivative, substantial derivative, material derivative. We call this the left hand side. We call this the total derivative. We call this the substantial derivative. Okay, or we call this the material derivative. And look at this one. Now this is the partial derivative. So we have used the change rule, and you can see then partial the change in y, the temperature. We are observing the particle temperature. We are observing the particle temperature. Lagrangian approach, individual particle we are observing, not a region. And now we have to relate this to the region, because I already mentioned that this is not physical for the experimentalist. Okay, or for the laboratory person to study the temperature changes of the individual particle, but it will prefer to uh, to study the temperature in a region. Okay, just like in a room, not to study the temperature of molecules of each and every molecule inside the room, because you can see in the room, if you can you imagine that if one grain of sand accommodates thousands of particles, so how many particles there will be inside when we consider a room. Okay, so there will be a billion and billion of molecules, and it is not possible to study each and every molecules. So we will study, for example, the temperature of the fluid particles, which will be the temperature of the room. Okay, so this is the temperature. And look at this one. Now we are studying the individual particles, so we will study the temperature, that what will be the temperature if it is moving in the x direction, if the particle moves in the x direction. So the changes in temperature in x direction, and then the changes in x with respect to time. Okay, similarly partial t by partial y, and again I have used the chain rule, dy by dt. So dy will be cancelled. Okay, so again we will have partial t by partial y, and similarly partial t by the change in temperature in z direction, and then dz by dt, and plus you can see partial t by partial t. Okay, look at this one, x of t, the change of temperature in x direction. So dx by partial t by partial x, partial t by partial y, partial t by partial z, and partial t by partial t, this t. Okay, so that's why we have this one. Okay, also partial t by partial t, and this is the partial derivative. This is the derivative, and this derivative is only possible for a point. Okay, we are using actually the Euliern frame of reference. We fix yourself at a point and trying to mirror the rate of change of temperature at a fixed point, that is partial t by partial t. Now you can see the term is this one. This partial derivative you can see is only for the fixed point. This is the slope of a point. You can see partial t by partial t. Okay, so when you uh, okay, the change at a point in the change in a point can be written this one. Okay, can be shown mathematically from this term, which is called partial t by, this is the partial derivative, first order partial derivative. Okay, so what does it mean, this point? This is very important thing. Okay, this only this expression, this term shows that we are studying the temperature at a point. So at a point means a fixed region. So when we say a fixed region, so the Lagrangian approach has been transformed to fixed region. Now you can see we can change this into a more appropriate form. Look at this one, partial t by partial x, and what is dx by dt? Okay, the rate of change of displacement. So this is the rate change of displacement. This is again the rate of change of displacement, and this is the rate change of displacement. So what is called the rate of change of displacement? The rate of change of displacement is called velocity, but this is the velocity in x direction. This is the velocity in the y direction, because the fluid particle is also it is moving. So this is the velocity, the displacement, the rate of change of displacement. So this is the velocity in x direction, and we denote the velocity in x direction from u component, the velocity in y direction from v components, and the velocity in z component from the w components. So this equation has been changed to this one. Okay, u partial t by partial x, v partial t by partial y, and w partial t by partial z, plus partial t by partial t. Okay, so now you can see this. Uh, this term, this derivative shows the changes at a fixed point. The changes at a fixed point. This is shows the changes of individual particles, not changes at a point. But this shows the changes at a point. So the Lagrangian approach has been transformed to the Euliern approach. Okay. The Lagrangian approach is changed to the Euliern approach. So this is all about these two approaches, Lagrangian approach and the Euliern approach. And in other way we can define this. I have already mentioned that this is called the material derivative or total derivative. This part this part is called the convective part, and this is called the local part. Okay, so the total derivative can be expressed as the total or the material derivative d by dt of any property dot means any property of the fluid. When we okay, so this will be the sum of the u partial by partial x of this dot. You can change this dot to velocity, to density, the fluid, any change in the fluid property. Then v partial by partial y plus w partial by partial z, this property, and plus partial by partiality of this property. Okay, so you can see uh, this part this part is called the convective part. So the total acceleration is the sum of the convective part convective, and this part is called the local part. So the total derivative is the sum of the convective derivative and the local derivative. Okay, and I told you that this dot is actually any property. So it means that if this is velocity, so you just change here. This is velocity. This will be velocity. This will be velocity. This will be velocity, and this will be velocity. And if you want to change this the rho, so d rho by dt is equal to partial rho by partial x, partial rho by partial y, partial rho by partial z, partial rho by partial t. Okay, so this is another way that when we change the Lagrangian approach to the Eulerian approach, so we actually doing that we are splitting the total derivative into the convective derivative and the local derivative. Okay, so this is these two methods. So now we have another topic to discuss for this week, and that is very important. That is the basic types of lines visualizations. Okay, so we have this sorry okay, so let me show this. There are some, you will see some I have explained this in the slides, but I will explain just I will show this topic and then I will explain from this PDF. Okay, so let's wait for a minute to open these slides. And okay, okay, so these are I have already discussed this, that we have this is the on the slides we have the two uh, description of methods of description, which is already given in the previous lecture. Lagrangian methods following individual fluid particles as they move. Okay, the fluid particles are tagged or identified. Okay, and determining how fluid properties associated with these particles. So you have to to watch this video. Okay, watch this video. This will give you more information about these methods. And this is the Euliern approach. Use the field concept, and the motion is given by completely prescribing and necessary properties, the function of space and time. What happens in the fluid properties at a fixed points in a space as the fluid flow passes to those points. So for this you have to watch this video. Okay, so these are the two videos, Now we have to come. These are the basic line visualization. So these are, you can see the uh, uh, this already that I have mentioned in the PDF. Okay, I have explained this in the PDF, but there are some links only. I have provided these links. So for this, I have shown you these links. Okay, to, yeah, maybe one is this and this is, these are two different. So you can also um, watch these videos. Okay, so let me minimize this and just go back to our topic. So okay, the same basic type of line visualization, you can you can watch the videos and it will explain in more details this topic. Okay, so these are some basic types of lines. Okay, we said that the line visualization of the fluid particles, uh, how the fluid particles moves. Okay, so as you can see, these are the visual of the lines. Okay, while the fluid particles move. So we have different types of lines. So the first one is the streamline. This is an imaginary line everywhere tangent to the local velocity vector. An imaginary line everywhere tangent to the local velocity vector at a given instant of time. So what is a streamline? Streamline is an imaginary line because the fluid in the velocity field, you cannot see these lines. Just like when you talk about the uh,
Hello friends, today in this session I will be talking about streamline, pathline and streak line. At the end of this video, you will get the clear idea about what are streamline, pathline and streak line and how they are different from each other. Let us first understand what are streamline.
okay, so what is a streamline? An imaginary line everywhere tangent to the local velocity vector at a given instant of time. So what is mean tangent to a point? Tangent to a point shows velocity vectors. Okay, tangent to a line shows velocity vectors, and local velocity vector on different points, different tangent lines show the locality. On different points, different tangent line show the locality. So we call this the local vector velocity. Okay, so when we call this the local velocity, if it shows different velocity on a different points. So look at this one. This is the velocity field. You can see how to draw. Okay, so this is the 2D field. You can see, and the fluid particles are moving in this region. So this is a snapshot. Okay, you can see the particle is moving. This is a particle A, and you can see that the velocity vector is tangent to the this line. The velocity vector is tangent to the line. Okay, So these the line to which the velocity vector is tangent, so that line is called the streamlines. So you can see this is the line. If the fluid particles, this is the line. So this line will be called the streamlines if the velocity is tangent to this to the different point of this lines. Okay, or the line which is which is formed or drawn to all the points which connects all the points where the velocity is tangent to it. Okay, so this is the velocity tangent to this line. So all the points when we connect, so this line is said to be the streamlines. Arrows are tangent to these lines. Okay, so you can see then this is the xy plane. The fluid particle is moving in this direction. Okay, so we call this streamlines. How to derive the equation for streamline? Now we are going to derive the equation for streamlines. Draw a random line of streamlines. Look at this one. This is a streamline, and the velocity is tangent. Okay, if you look at here this line, so the velocity is tangent to this point. The velocity is tangent. So the line, okay, which is tangent to these velocity vectors are called streamlines. Direction of a fluid particle. Okay, this is the fluid particle is moving in this direction, and this line has been drawn while joining the different points where the velocity vector is tangent to this line. Okay, so you can see at this point A, if this is point A, okay, so at this point this is the function of x and y, but after some time when it reaches to this point, you can see at this point it covers some distance, so it becomes the function of x plus dx, y plus dy. Okay, because it covers some distance in x direction and y direction. So the velocity field is given as uv and w. So let me consider this is the velocity field. Okay, so this is when we say that the velocity field, so the fluid particle is moving. Okay, this is the velocity field. Okay, the fluid particle is moving in this direction, in this xy plane, in this xy planes. Okay, so we call this the velocity field. This is only in the 2D case, but in the 3D case we will also have the fluid particles in the z directions. Okay, so this is the velocity field. The fluid particle is moving in x direction, in y direction. The velocity of the fluid particle in x direction is u. The velocity of the fluid particles in y direction is v. The velocity in the z direction is w. Where the tangent position vector is dr, dx, dy, dz. Okay, so this is the position vector. Position vector is denoted by from dr. Okay, so the velocity vector tangent, the tangent line, this is dr actually. Okay, you can see, so the velocity vector and the tangent line are coincide each other. Okay, they are same velocity vector and position vectors. So the tangent line is called, this line is it's called the position vector, denoted from dr, and dr is equal to dx in x direction, y direction, and in z direction. So as dr and v are collinear, okay, you can see both are collinear. Okay, so and at this point, this is the velocity, and the same time this is the position vector. Okay, so both are collinear. As dr and v are collinear, the angle between v and dr is 0. Okay, of course you can see the angle between v and dr. What is the angle between? This is v. Let's say this is v and this is dr. This one is dr. So what is the angle between these two vectors? Of course it is 0. Okay, as dr and v are collinear, the angle between v and dr is 0. The cross product of velocity and position vector v cross dr is equal to v dot dr sine theta. Just like a cross b is equal to ab sine theta. So a dot b, a into b sine theta. So as the angle between this is 0, so sine 0 is 0. So v dot dr is equal to 0, and this is vector, so it can be written as 0i, 0j, and 0k. So now find v cross dr, the cross product ijk. So you can see is equal to 0. So find the cross product, and we have v dz minus w dy, I minus u dz minus w dx, j plus u dy plus v dx, k equal to 0i, 0j, and 0k. Now compare the coefficients of I, j, and k. We have I on the left hand side and also I on the right hand side. So you just compare I with i's, j's with j, and k with k. So we have v dz minus w dy. Look at here, v dz minus w dy is equal to 0. And we can write this v dz is equal to w dy. So rearrange this, and we have dz by dy, dz by dy equal to w by v. So this is the equation of streamline. The equation of streamline in the yz plane. If we have z and y, so it is called the yz plane. And you can see in the velocity in z direction is w and the y direction is v. So this is yz plane. Okay, the streamline the yz plane, and we can write this. We can rearrange this one. Dz by w and dy by v. Similarly, compare the j component of both sides. So we have dzw by dxu. So you can see z and x, so xz plane. And similarly, the third one is dxu and dyv. Okay, sorry, this one dyv is equal to dxu. So y or xy plane. Okay, xy plane. So if you look at we have dy by v is equal to dx by u, but dx by u is also equal to dz by w, and dz by w is equal to dy by v. So actually all these three expressions are equals. So we can write this relation as dx by u is equal to dy by v equal to dz by w. Okay, so this is the relation for the streamline, and these are the equation for the streamline. Now we have a velocity field. So this is called a velocity field u in x direction, the velocity field, and In y direction, the velocity field is y. U is this and v is this. Find the streamline at instant of time. So we have to find the streamlines, okay? So how to find the streamlines? So we have this relation because this is the xy plane, okay? uv, the x direction, v the velocity in y direction. So we have to consider the xy plane, that is dux dx by u equal to dy by v. Okay, so this can be written as dy by dx is equal to u by v, sorry, v by u. Dy by dx is equal to v by u, and we can write this dy by v and dx by u the same, okay? So you can see here dy by v, so we have v is equal to y and u is equal to x by 1 plus t. So put the values of v and u, we have dy by y and dx by u, which is x plus 1 plus t. So it can be written as dy by y is equal to dx 1 plus t x. Integration both the sides, we get ln of y, and this is dx by x, so 1 plus t ln of x plus ln of c. So this can be written as ln of y ln of x using a power rule, and this is the uh, we have logs and we have plus between these two expression, so we can apply the product rule. We can write this as the product rule, ln of c x1 plus t. So ln will cancel, and we will have y is equal to c1 plus t. So this is actually equation for this streamline. Now you can draw these streamlines, okay? So I have drawn roughly this streamlines for, this is x, so for x is equal to 0 and for c is equal to 1. So this is the line when x is 0, okay, and t is 0. So when t is 0 we have cx and c is 1, so y is equal to x. We have y is equal to x. When t is 0 and c is 1, so we have the relation y is equal to x. So you can see this straight line, y is equal to x, or c is equal to 1 and t is equal to 0. And when c is 2 and t is 0, so we have 2x, and this is line for the c2. For t is equal to 1, we have these two lines, okay? Here are some properties of the streamlines. That, remember, two streamlines do not intersect each other. Okay? Two streamlines do not intersect each other. And how? It means that the fluid particles at c will have, if it intersect each other, let's say these are the two, one is a streamline and one is b streamline, and they are intersect each other. So here you can see, look at this point C. So the velocity, one velocity vector is in this direction and one velocity action is in this direction. Okay, so it means that the fluid particle at C will have two velocity directions. Okay, look at the reason. Now it means that the fluid particle at this point has two velocity direction. The velocity, because this velocity is only one direction, it will move in this direction or it will move in this direction. So when it crosses each other, so it will have this direction, also it will have this direction. So at C will have, okay, two velocity directions, which is impossible. It is not possible that at one point the velocity be only in one direction. There cannot be any movement of fluid mass across the streamlines. So this is the second property, is that there cannot be any movement of fluid mass across the streamlines. Okay, so there is no movement across the streamlines. Okay, now the path line. This is another type of line. The first one was a streamline. Now this is the path line. Actual path traveled by a given fluid particle is called path line. Path line is actually the actual path traveled by a given fluid particle is called a path line. Or a path line follows the movement of a single fluid particle. A path line follows the movement of a single fluid particles. So when we say about that it is a single particle approach, so of course it is a Lagrangian approach, as we observed that the individual particles move from one point to another point in the fluid field. Okay, so this is the actual path traveled by a fluid particles. Okay, so for example, this is the fluid particle. This is the fluid particles, and the fluid particles move, okay, like this here, and then come like this and this. So this is this fluid particle. This is the path of this particle. So this line is said to be the path line. Okay, so this is the way, okay, when you observing the fluid particle and it is moving like this, so that path that traveled the particle, so that path or that line is called the path line. Okay, and it is already said that it is uh, showing the individual particle, considering the individual particle. So this is the Lagrangian approach. Look at this one. At some time t, the particle was at position A, but you can see after some time, okay, at point A, at point t, okay, the particle position was at A, but after some time t, d plus dt, it reached to this position. Look at this position, okay, and maybe after some time t, it will reach to this position. Okay, so look at this one. This is the initial time, and this is after some time t. Initially, the time interval is from t naught to t. Okay, t is equal to t naught. Look at x is equal to, this is the distance is equal to the particle position at t. Particle position at a at time t. Okay, so it can be written as x minus xa t equal to t naught. So the range between the limit between these two is t naught t and u dt. Okay, velocity in time t, and the range is from t naught to t. Similarly, in the y direction we will have y minus y. 8 is equal to t naught. This is t naught, and t naught to t v dt. And in the z direction, z minus za, and it is from t naught to t w dt. So these are the equations for the path line, and a path line can intersect each other. Okay, because it is the individual particle, the movement of individual particles. So individual particles can start moving from this direction and then come like this and then move like this and then move like this. Okay, so it can do random movement and can intersect each other. Unlike the streamline, a path line can intersect each other. Okay, so again we are going to find the path line of the same uh, for the same velocity particles. The velocity particles also have the streamline, but now what will be its path line? Okay, the previous one was the line where the velocity was tangent to that line, but in this case, this is the real path of that individual particle. So we have to find the path line. Okay, and the time interval will be from time 0 to uh, t. Okay, the time will be t is equal to t naught equal to 0 initial time. Initially, so we have this velocity u, this is u, and now we are studying the path line. So actually it is the particle velocity. So we will just mention up, the particle velocity, and it will be xp, the distance of the particle, of the individual particle. So just change, just we mention to differentiate this. Okay, up, the particle velocity, and xp, the particle distance, and this is the velocity. So according to the velocity definition is the rate of change of displacement. So we can write dxp by dt. Okay, and it is equal to x by 1 plus t. Okay, x by 1, it is already given. So just we have written this, the velocity in this form, dxp in the displacement form. The rate of change of displacement is velocity, and it is equal to, it is given at this one. Okay, and similarly in the y direction, dyp is equal to dt is equal to y. So at t is equal to 0, x is equal to x naught and y is equal to y naught. The displacement, the distance is x naught when time is 0. So the particle is at this position and in x direction, and the particle is this. It means in the 2D plane at a point, this a point is x naught and y naught. Okay, okay, this is already okay. So I think this is the fair one. That one was, there was some mistakes. So again, okay, up is dxp by dt, which is equal to x by 1 plus t. So just okay, change separable variable dxp by dx and dt by 1 plus t. Okay, and the range is 0 to x, and this range is 0 to t. When the time is 0, so the distance is x naught. So look at this one. This is dx by x. So it is ln of x, and the range are from 0 to x, and this is dt1 plus t. So its derivative is dt, so its integral is ln of 1 plus t, and the range is 0 to t. Okay, so this becomes the upper range minus lower range, ln x minus ln x 0. So this should be 0. Okay, ln x naught. And when the time is 0, so this is x naught. Okay, so this is from x naught to x. This is not 0 actually. From x naught to x. This should be correct. This is x naught. Okay, when the time is 0, so the distance is x naught, and after t, its distance is t x. So ln x minus ln x naught, and first limit, upper limit 1 plus t, and the lower limit is ln 1 plus 0, so it becomes ln 1 and it becomes 0. So all we have only ln 1 plus t. Okay, so the left hand side can be written as this is the negative sign subsection. So apply the rules. We can write as ln x minus by x naught division. Okay, so cancel log from both sides, and now we can write this x in equal to x naught, and this is the path line in x direction now. Okay, the fluid particles move in x direction, and you can see it satisfies the condition when time is 0. So then the distance is x naught. Okay, and now in the y direction we have dy by dt. So we have dy by dt is equal to v, which is only y. So separate the variables. So we have dy by y is equal to dt, and now apply the integral on both sides, and the range from y naught to y, and from t0 to t. Okay, so this is y naught. Okay, sorry, this is y naught to y and 0 to t. So you will have the same. This will be only t, and this will be ln 1 y naught, and y is equal to y naught e power t. So now this is the particle path in the y direction, and also in the equation 3 we have the particle line in the x direction. So path line is the plot between x and y. Eliminate t to draw the path line. We have to eliminate t. Okay, so from equation 3 we can eliminate t, and then we will put in equation 4. Okay, so we have y is equal to y naught e power x by x naught minus 1. Okay, when x naught is 0.5 and y is 50. When x naught is 0.5, this implies that y is 50. Look at here. When x naught is 0.5, so x becomes 0.5. This is, and y is almost 50. So you can see here. So these are this is the path line. Okay, the path line in the xy plane. So these are different path lines, because if you differ x naught values, so you will have different path lines. So you can see, okay, this is x and this is y. Okay, x and y. So the third one is the streak lines for the unsteady flow. Okay, when time is involved. So what is now a streak line? A streak line is the line joining the fluid particles. The streak line is the line joining the fluid particles position, or the fluid particles that once earlier passed through the same fixed point in space. A streak line is the line joining fluid particles that once earlier passed through the same fixed point in the space. Okay. Now let us consider, let's understand the concept of the streak lines. Use the current time as a reference times. The current time. Okay. Look at this one. This particle A is now at this position A, but initially it was at point P. Look at this one. You have to go back. Okay, go back to, this is the memory effect. Okay, now this particle at this point, but before, sometime earlier, it was here. Actually, it comes out from this this point. Okay, and this point, this particle now at this position, this is another particle B. This particle B was also sometime earlier were at this position, but now it is at this position. And this particle C now at this point position, but earlier it was at this position. So what does it mean? Initially they were at the same point. Okay, they passed from the same point, but now they are at different positions. So this is the very physical example in our daily life, when the smoke is out from the chimney. So if this is chimney, okay, so the fluid or the gas is out from the chimney, so that this point is, you can see, okay, this is the chimney, and when the smoke leave the chimney, so the fluid particles then scatters in different direction. Okay, so after some time you will see that the fluid particles, before, all these particles were here, but now when it leaves this position, they are scattered in different and located in different position, like A, B, C and D position. Okay, so this is called the streak lines. So now if we join these particles line, so this will becomes the streak lines. From here to here, this is the path line of this particle. This is the path line of this particle. Okay, but when we join all these path lines, so then it becomes the streak lines. Okay, so initially it was at position this, but now they are at different positions. They are come out from all from this position, but now they are located at different position. Particle A passed through point P at earlier this time t minus dta, because it is memory, so we call we write this in t minus dta. Some earlier time the particle passed through this point, this particle okay, passed to this point P at some earlier time of t minus dta. Particle B at t minus dt, okay, passed through a point P at earlier time this, but now they are at this position. Before, all these particles were at point P. Now they are at different position, but if we minus this time from this one, so they will just come to position P. Okay, if we replay, if we come back to, okay, if we allow the visualization to go back, okay, so it will come here, all these particles will collect here, and then they will scatter and located at different positions. This is the same like someone smoking. Okay, so when it allow the smoke uh, to leave from her mouth. So, okay, so his mouth is just like a point of where they are located. All the particles are located at the same point, but when it leaves the mouth, okay, so the smoke scatters and moving randomly in various direction. So then you can see that smoke leaves from the same point, okay, but now they are at different position. So we call this the streak lines. When the particles, when that different particles line we meet, we connect, so we get the streak lines, okay. All the fluid particles A, B, C, D currently at different positions, but earlier they were at same point P. To draw the streamlines, we have, again, now we have the same problem, and now we are going to what will be the streak line of these particles. So we have already calculated these: x is equal to x naught and y is equal to c2 et. Okay, from to draw the streamline, we have x is equal to c1 1 plus t, and c1, this is from the streamline. Okay, you can see where is c1. In the streamlines, from these equations we have eliminated the constant value and put, yeah, you can see here we just eliminate, okay, c value, okay. Yeah, we just eliminate c, and while eliminating c we have just incorporate x is equal to c1 1 plus t, so c1 is equal to x naught by 1 plus t naught. Okay, I think this is from, okay, so uh, when you put the value of c1 here, so you will have x naught 1 plus t 1 plus t naught. This is equation number 1, and y is equal to c2 e power t. I think this is from the path line. Okay, just we consider the two constants value, and we have this c2 constant value. So when we put replace this c2 by this value, we will have this one. Okay, so y naught e power, we can write this e power t minus t naught. Eliminate t naught from equation 1 and equation 2. We have t naught here, and also we have not t naught also here. Okay, t naught is the reference time. So you can see t naught, eliminate t naught. I just found that t naught value from x and then incorporate in y. So now x naught is the distance at when time is 0. So now you can draw the streamline by putting these values. You can see, okay, this is x and this is y. T naught is the time of particle where the particles were at position x naught y naught, and t is the time which varies along the path line. So a path line from t naught to current time t, you can see this one, okay? Take x naught y naught is equal to 1 1 and t is equal to 2, t naught equal to 0. To get xy for t naught equal to 0 and t naught is equal to 2, you can see these lines are, okay, x naught and y naught equal to 1 1. So when you take this one, okay, so these are the different, you can see, look at this one. This is the path line of this particle. It is move, okay, this is, and this is the path line of this particle, and this is another particle path line. And when we join this line, which join this particle, this is called the streak line. Now this is called the streak line, okay. So also I have some there are some uh, videos about these lines. Remember one thing, that for the steady flows, all these lines are equals, okay. When the flow is steady flow independent of time, so what will happen, okay, okay, for example, if these are some are the in the steady case, you can see the streamline will be this one, the streak line will be this one, and the path line will be this one, okay. So in the steady case, the the streamline will, and the path line and the streak line will be same, okay. So the only difference that is produces, that is now in this case, that will be uh, and now if this is the path line after this particle, and this is the path line of another particle, and this will be the streak line. So in the unsteady flow they will be different, but for the steady flow all the three line will be same, okay. So uh, but for this is important to watch this video. It is very important one, okay. The flow visualization. So when you watch this video, you will see the difference between the uh, streamline, streak line, and the path line, okay. So please watch this video and then discuss with me if you have any uh, problem, okay. So we will discuss. I will remain at your disposal when you have any query or uh, ambiguity, so you can discuss with me, okay. So this is the end of this lecture. It already took a long time, so I have to I wind up these lectures, and if you have any ambiguity or queries, so we can discuss this, okay. So thank you very much.